My name is Dr. Esther Trufan, and in this video, we're going to explore some of the applications of calorimetry. Specifically, we will be looking at heating and cooling processes. In the context of calorimetry, we need to remind ourselves that calorimetry is a technique through which we measure heat that is exchanged between two different chemical or physical processes. It usually involves a calorimeter, which is a specially designed apparatus. The most commonly used apparatus in the chemistry laboratory is the coffee cup calorimeter. This requires two nested styrofoam cups, which ensures the insulation of the system, usually a cover of some sort that minimizes the chance of heat escaping through the top of the cup. Usually it requires a thermometer to measure the temperature at the beginning and at the end of the process, and some kind of stirrer to ensure that the temperature is homogeneous across the calorimeter. What we find then is that most experiments are done in some kind of water-based media, and through the thermometer, we're going to monitor the temperature changes of the water. It should be fairly straightforward then to calculate the heat associated with what happens to the water. Then, because the calorimeter is an insulated system, the energy that is associated with the water, or the heat associated with the water, will have to be the same value, but going in the opposite direction for the other process that is also taking place in the calorimeter. One example of a calorimeter being used in a heating or cooling process is where one would take a hot piece of metal and drop it inside a calorimeter with water at a known temperature. You would then leave the calorimeter to achieve thermal equilibrium, which simply means that both the metal pellet and the water are going to have the same temperature. And this naturally occurs after some time. In the first step, you would start by determining the heat associated with what happened to the water. If we have most of the information provided, then the heat of the water is going to be the mass of the water, in this case 100 grams, times the specific heat of water, which is in the liquid phase, and we know it to be 4.184 joules per gram Celsius, times the final temperature of the water, which in this case it is 38.6 degrees Celsius, minus the initial temperature of the water, which is the 25.1 degrees Celsius. If we complete our calculation, we find that the water absorbed 5,648 joules worth of heat. In the next step, before we can approach the calculation associated with the heat capacity of the metal, we need to determine how much heat was released by the metal. In this process, we need to remember how our calorimeter functions. It's an isolated system. However much heat the water absorbed had only one source, and that is the metal. So if our water absorbed 5,648 joules, then our metal pellet is going to have the same value, but with opposite sign. The heat of the pellet is going to be the heat of the water with a negative sign, so a minus 5,648 joules. Once we determine the heat of the pellet, if we know its initial and final temperature and its mass, then it should be relatively easy to determine both the heat capacity and the specific heat. This problem requires us to calculate the heat capacity. Now, heat capacity is Q equals C times delta T. where C is heat capacity. And if we place a P subscript to indicate that all of these are associated with the metal pellet, it will be more straightforward for us to calculate it. The heat of the pellet is minus 5,648 joules. This equals the specific heat of the pellet times the temperature change. The final temperature of the pellet is 38.6 degrees Celsius, and the initial temperature of the pellet is 135.0 degrees Celsius. If we divide both sides of the equation by the 38.6 degrees Celsius minus the 135 degrees Celsius, then we will find that our heat capacity equals 58.6 joules per degree Celsius. And it makes sense for our heat capacity to have a positive value because it means that every time we warm an object, we need to give it heat. And every time we cool an object, we need to remove that heat. The negative sign for our heat will then always come from the temperature change. If the temperature goes down, the associated heat value will also need to be negative. Another way to approach this problem is to determine the specific heat or specific heat capacity of the metal. For that, we start the same way. First, we calculate the heat associated with the water. In our case, we have the heat of water be equal to the mass of the water, which is 100 grams, times the specific heat of the water in the liquid state, which is 4.184 joules per gram Celsius, times the temperature change associated with the water, which is 38.5 degrees Celsius, minus the initial temperature of the water, 25.0 degrees Celsius, giving us a heat of the water of 5,648 joules. From here, we can move on to our second step and determine the heat of the pellet. Because we're working inside a calorimeter, we know that there was no heat lost if proper precautions were taken, and the heat of the water is going to be the same as the heat of the pellet with a negative sign. Or the other way, the heat of the pellet is the same as the heat of the water with a negative sign. Both of these will tell us that the heat of the pellet is negative 5,648 joules. To determine the specific heat of our metal pellet, we need to simply place the heat of the pellet into the calculation. The heat of the pellet will be mass of the pellet times the specific heat of the pellet times the final temperature minus the initial temperature of the pellet. The heat of the pellet is minus 5,648 joules. The mass of the pellet is 15 grams. The specific heat of the pellet is unknown, so we keep it as its symbol. And the final temperature is 38.5 degrees Celsius minus the initial temperature, 130 degrees Celsius. We divide both sides by the 15 grams times the temperature difference, which is negative 91.5 degrees Celsius. And this will tell us that the specific heat of the pellet is 4.12 joules per gram Celsius. This approach will give us a systematic way to determine the specific heat associated with any metal that is heating or cooling in a calorimeter that has water in it, the temperature of which is carefully monitored through the experiment.